So we're back with class 2, and here's an example of dependent motion and relative motion. It's sort of from my book. Actually, the one in my book is a little bit different from this, but I tried to make something that's kind of complicated, and I'm able to confuse myself as well. So I'll try to take this slowly, methodically, and logically, right? So block A starts from rest, and Newt Dog and Wormy are connected by cables and pulleys to block A. So they're dependent on them, therefore they must start at rest as well. And it moves downwards with a constant acceleration, right? So it's going down, and we have to decide which way that Wormy and Newt Dog are going to be moving based on that. So somehow we happen to know from observation that after 5 seconds has elapsed, that Newt Dog, the velocity of Newt Dog relative to Wormy is 8 feet per second. And we don't know, by the way, whether that's up or down necessarily, like which one is greater than the other, but we will decide that by way of this dependent motion. We want to determine the acceleration of A, right? So this is a complicated, well, not complicated problem, but it's a problem that that's potentially confusing. I think the best way to do is to start off with a datum right here, right? And we're going to use that as a datum. We're going to call this one xn from here. We're going to call this to xa is going to be the distance to A right there, or we could say like right to there, so I guess. And then here is going to be xw, right? So let's figure out this. You see that there's two ropes. There's one rope, and then here's the other rope. So let's write out the two equations for the two ropes. So the length of the rope is going to be xn plus xa, right? There's only this length and that length right there. For the second rope, we're going to go this length, and this length. So there's three. Did that right? 3 xa's, and then there's 1 xw. So if we take the time derivative of these, we get vn plus va and 0, 3 va plus vw. Which, by the way, we note that Vn is equal to negative Va, and that 3 Va, or maybe I should write it out this other way, that Vw is equal to negative 3 Va. Okay. That's over to the side. We also say for the acceleration that we have the acceleration n plus the acceleration of A, right? And 3 times the acceleration A plus the acceleration of W. All right, so we did the dependent motion relationships. Now let's take a look at this other piece of information. Knowing that after 5 seconds, the velocity of Newt Dog relative to Wormy is 8 feet per second, right? So that's the velocity of Newt Dog with respect to Wormy, as an NW, is going to be equal to 8. But we don't know whether that's positive or negative necessarily, right? We can, though, write out that this right here is equal to this after 8 seconds. So we can figure out what the acceleration is, right, of these two with respect to each other. Oh, by the way, let's just for a second say that we know that with these two equations right up in here, let me combine those together. So we could substitute, let's say, negative Vn, right? So if we have Va right here and we substitute negative Vn, it becomes positive. So we know that the velocity of Wormy is equal to 3 times the velocity of newt dog, and they're not negative. So these guys are moving in the same direction. So they must be moving upwards because A is moving downwards. I think that's true, right? You could see that from here, newt dog and A are moving in different directions. So this one's moving down and he's moving up, right? So that means one of these is traveling upwards faster than the other one. Well, which one? Well, Wormy is going upwards faster than newt dog, right? You buy that? Right? So Wormy is going faster, 3 times faster than newt dog. So the relative velocity of newt dog with respect to Wormy has to be a -8 because he is traveling less, right? You could even say that, like, because we know that this is going to be, let me put it another way here, that the velocity of newt dog with respect to Wormy is equal to the velocity of newt dog minus the velocity of Wormy, right? So just recognize that he is traveling faster than him, so that's going to be a -8, a negative number. We can write out this equation right here for a constant acceleration. We're told it's a constant acceleration, so all of them have to be a constant acceleration. So we could say that the original, this is O, that's the starting velocity, plus the acceleration of dog with respect to Wormy times time, right? So we know that this is -8. We know this is 0. So we could say this -8 is equal to 0 plus the acceleration of newt dog with respect to Wormy times 5 seconds. And what we end up finding is the acceleration of newt dog with respect to Wormy is equal to a -1.600 feet per second squared. Right off the side of the page. Right? So another thing that we can, so here is an actual value that we can place into with this, because we're looking for acceleration, right? We determine the acceleration of block A. So what we could do by putting this in here, we could say that the acceleration of newt dog with respect to Wormy is equal to the acceleration of newt dog minus the acceleration of Wormy, which is equal to -1.600. Right? And so the acceleration of newt dog, when we could substitute, let's see which one, we never wrote it out. Yeah, I did for the velocity, but I didn't. I'm kind of messing this page up here by jumping around. But let me write also here that the one second, when we combine that one and that one together, we find the acceleration of Wormy is equal to 3 times the acceleration of newt dog. That's where I did. Okay. And so now we can use that and substitute it in for here. So minus 3 acceleration of newt dog is equal to -1.600. And so now we have the acceleration of newt dog is equal to 0.8 right there. And feet per second squared, and that must be going upwards, right? Because the acceleration of A is downwards, right? The A is moving downwards, so newt dog must be accelerating upwards. And because we know that this relationship exists right here, right? The acceleration of newt dog is equal to the acceleration right here. Negative. Well, they should be negative from each other, so they're in the opposite direction. We end up getting acceleration of A is equal to 0.800 feet per second squared and I'll draw it with an arrow. Boom. Downwards, just like they told us. Now, we could also go back and find what the actual, I believe we could go find what the actual values are going to be, because, they're just relations. The kinematic relations here. We could just say, if we know the acceleration of A, we know the acceleration of Newt dog. Let me say, we know the acceleration of Newt dog, therefore we can find what its velocity is going to be, because it's also constant, right? So we could say that the velocity of Newt dog is equal to the initial velocity of Newt dog plus the acceleration of Newt dog times time, because we know that it's constant. We know that it is going to be, he's going to be going upwards right in there. So, and we know that that's 0. If he has plus 1.600 times 5, is that going to be like 1.65 times? That's going to be 8. No, that was stupid. Okay, so so that's 8 feet per second. Oh wait, does that make sense? Yeah. No. That's supposed to be 0.8, dummy. All right, so that makes like 4, right? Yeah, 4 feet per second. So Wormy's velocity at that time is just going to be 3 times that, right? So 12. And we know that the velocity A is going to be moving 4 feet per second downwards. So we have the things sorted out. Hopefully I didn't jump around too much, and that you can follow the logic or the process of trying to walk through these related things, right? These are the key to this, but also this basic equation right there. That basic equation really kind of tells you a lot. And note that we can also make the relative velocities and acceleration will also work through this basic kinematic relationship right there for the case of a constant acceleration. So there you go. There's an example. And you should take a separate piece of paper and try to work it out yourself and make sure that I got it all right. But I think it's right this time.